Hello friends, welcome to today's class. So today we'll start with our new topic, which is called as multiple random variables. We'll discuss with the multiple random variables. In till today we have discussed your single random variables, and moving ahead with today's class, we'll go ahead and try to discuss what are this multiple random variables. Okay. So single random variables, friends, you have already seen your various things regarding your single random variables. You have seen how to find its PDF, how to find its CDF, and their various properties, as well as mean, expectation, variance. All those things have been discussed in the previous classes. Today we'll move ahead and we'll try to touch upon this multiple random variables. Okay. So in order to understand your multiple random variables, one very important thing we all should know is our CDF and PDF equations. Okay. So if you remember our CDF and PDF equations, I hope you know that your CDF is nothing but it is given by what now? It is capital F, it is capital, say F small x, here it is, yeah, so F small x followed by capital X here. So this is your CDF, this you already seen for a single random variable. Similarly, you have also seen your PDF, which is something like this, that is small f of x, okay, and into the bracket capital F of x. Okay. So this we have already seen in all the previous classes. Now moving ahead, when we say that we are speaking of multiple random variables, the other name for your multiple is bivariate. Bivariate is nothing but we have two variables. That's why we call it as bivariate. So which are our two variables? Our two variables are x and y. And always remember friends, this x and y will be in pairs. They will come together. Okay. Now in real world, what are the examples of your bivariate random variables? Like say for example, we give an input to a system. We give an input to a system at some time instant, say t. Then we represent it as a random variable x. So this is our one variable. Similarly, what is the obvious thing now? When we give any input, we would also expect the output. So we will be expecting the output at a different time instance, say t2, and this output is represented by a random variable y. So always remember friends, this x and y will come in pairs. It's quite obvious, whenever we give input, we try to expect some output. So any input is represented by x, any output is represented by y. So such things are represented with the help of your bivariate random variables, or the other name is multiple random variables. Okay. So another very beautiful example we have is in our electronics and communication. Like say for example, whenever you send any signal, whether you want or you don't want, the noise will be produced. Okay. So therefore we would require two random variables to denote your signal and noise. Okay. So one of the things, that is signal, is represented by one of the random variable x. The other thing we have is noise. This is represented by another random variable y. Again here, no doubtably friends, even minimum noise is always present. Even when we are talking right now, even though it's quite silent, but still there is some minimum noise. Okay. So that means whatever I am talking, that is represented by a signal. Say if that is a signal, then that becomes x, and whatever the noise which is coming, that is nothing but your represented with the help of the y. Okay. So this is regarding your bivariate random variables, and what actually are your bivariate random variables, and how they are present in our real world. Now moving ahead, the next very important thing we need to discuss is our CDF, that is cumulative distribution functions. So CDF friends, we already know the CDF, that is if it is a single random variable, this is how you denote your CDF. Please concentrate. So you can see here that we have represented it with a single x. Okay. Why? Because there is a single random variable, and its definition is nothing but p probability of into the bracket capital X, which is less than or equal to small x. Okay. So when I have only one random variable, this is my definition. So we'll be extending the same definition for bivariate random variables, that is two random variables. Okay. So we have multiple random variables, right? Then those multiple random variables are what now? X and Y. So as we are speaking, this X and Y will always occur in pairs, and I have given you the examples as well here. Now in that, in your random variables X and Y, so Xj will be belonging to X, capital X, and Yj will be belonging to capital Y. So these two pairs will be belonging respectively to each of these variables. Okay. In that case, what would be our CDF is? Please observe here, it is nothing but it is just as I told, it is an expansion of your single random variable. So it is nothing but here we have only one random variable, that's why we have written here only one capital X. Here we have two random variables X and Y. So therefore you can see here we have defined two random variables X and Y, that is capital XY. Similarly, here you can see we have only one, so therefore only one small x, but here we have two, therefore x comma y. Next, for x this is my CDF, for y this is my CDF. Then what is total CDF? The total CDF is nothing but it is the intersection of the first variable along with the second variable. Now what do you mean by this intersection? This also we have already discussed in all your previous classes. It is nothing but it's like a AND operation. We'll try to get a common area, and intersection is nothing but we'll try to get a common area. Like say for example, if this is my x and say for example this is my y, okay, so what actually is intersection? It is an AND operation. Whatever you can see here in this thing, in this common thing, say this is my A and this is my B. So whatever you can see here in this common thing, this is nothing but your intersection. Okay, so that is what we are trying to do here, intersection. Okay, so this is the definition of your CDF for multiple random variables. Please remember this thing as how you had remembered this formula. This was used till now. Similarly, this will be using for a long time. Next very important thing, we will be trying to discuss some of the properties of your bivariate random variables. We'll try to look upon some properties. Now, one very important property which was also present when it was a single random variable and which is present now as well, that is your bivariate CDF is a non-decreasing function. And as very important thing which you need to remember here is, here we have two directions. One is for x and another one is for y. Why two directions? For the simple reason, because we have here how many variables? Two variables. So that's why we will be representing our variables in two planes. That is, one is x plane and another one is y plane. We'll be trying to take the help of both the planes. So therefore, your CDF is a non-decreasing function in both the directions, that is x as well as y. Very important. Next very important property, your CDF for both the random variables will be ranging between 0 and 1. So as we have spoken already that it will not go below 0 and it will not go above 1. Like say for example, if I have a minus infinity, if you recall from the single random variable, it would be what? 0. If I have a plus infinity, then it will be 1. That is the maximum value that we have seen for your single random variable. The same extension, the same property is also available for your multiple or bivariate random variable. Okay, that is nothing but f of xy, x comma y, and this CDF will be in between 0 and 1. Okay, now let us try to see, as I discussed just now, what will happen if the event is minus infinity, that is somewhere at the end after this, after 0, somewhere here. Now if the event is minus infinity, we call it as an impossible event, that is it will never occur. The meaning of impossible event is we will never reach minus infinity. Such an value is not possible. Okay, so now what we'll do is we will take our equation number 1. So here is our equation number 1. Okay, so using this equation number 1, we'll try to substitute your minus infinity. Okay, so what he has told, what we have taken, that x is less than or equal to minus infinity. So just substitute the value of minus infinity in place of x. Please observe here, we have substituted minus infinity in place of x, right? So what about y then? Y would remain the same thing. The y has remained the same thing. Okay, now whenever we say that x is less than or equal to minus infinity, as we just now spoke, that it is an impossible event. That is, it will never occur. So if it is an impossible event, we denote it by a null set, which is nothing but what you can see here. So always remember friends, one very important thing here, the null set and its intersection with any other CDF will be a null set itself. This is a very important property. That is, say for example, I have a null set, and when you try to intersect that null set with 1, you will be getting is what now? Your null set itself. It's like 0 multiplied by 1, you can say. It's not actually like that, but you can understand, or you can remember, like when we multiply 0 with infinity, the answer will be, sorry, 0 with any value, the answer you will be getting is 0. Something like that you can remember. So therefore friends, very important property, that is, when one of the variable is minus infinity, the answer I will be getting is 0. Similarly, as I said just now, here our one of the variable is x, right? So if my y is minus infinity, then also the answer you will be getting is 0. Okay, if your x is minus infinity and your y is also minus infinity, then also your answer will be 0. That means if any one of the variable is minus infinity, either x or y, or if both the variables are minus infinity, then our answer will be 0. So this is very important relation. Next very important thing we have is, so we have seen here what now, that x is less than or equal to minus infinity. The same relation we will enhance, or we will check for when x is less than or equal to plus infinity. So this means that whenever x is less than or equal to plus infinity, it is an obvious event. That means what now? It will for sure occur. So simple example here is, say you are taking the example of tossing a coin. So tossing a coin, right? So when you toss a coin, it is a for sure event that either you will get a head or you will get a tail. You will not, the coin will not be rotating forever in the sky. Is that right? Yes. The coin will not be forever rotating in the sky. It has to fall and it will give an outcome. So therefore, when we take x is less than infinity, it means that this event will occur for sure. So therefore, when it is going to occur, then it will be some point on my xy plane. It will be some point on my xy plane, right? So like say what I'm trying to tell you is, say this is my y plane, say this is my x plane, so this is x plane and this is y plane. So what we are taking here friends, we are saying that x is less than infinity and it has to occur. So when it has to occur, that means that it will occur and it will take some point in this plane, anywhere, it could be anywhere. So that is what has been explained here. Okay, so therefore again we will use our equation number 1. So here I have my equation number 1. If you want, I will take a snapshot of it so that it will be easy for us to understand. Okay, so we'll take our equation number 1. So from equation number 1, we'll be using our equation number 1 again. So what we have done here friends, we have used your minus infinity here. We'll move on. Okay, so what we have done here, x is less than infinity, so therefore we'll substitute in the place of this x, we'll be substituting what now? Infinity. Okay, so as we told you that this is a sure event, that means it has to occur somewhere in your sample space. So therefore the sample space is intersected, with y. There are no changes in y variable. So always remember friends, when you intersect the sample space with the other event, the answer will be other event. So I hope so it is clear. When you intersect a sample space with an variable, the answer will be an variable. What is happening here? When you intersect a null set with a variable, the answer is a 0. What you can remember this as something like this. It's 1 multiplied by 5. So when you multiply 1 with 5, the answer is 5. This is nothing but 0 multiplied by 5. So when you multiply 0 with 5, the answer is 0. Okay, so that is what has been given here. So you can see here, when one of the variable is infinity, here x is infinity, then our answer or the output will be the probability of the other element, not that element, the other element. Which element is infinity here? X. That means what will be our output? It will be the probability of y, which is the other element. Okay, so this is nothing but it is the CDF of y. So you can see, you can just correlate here this and this. This is the definition of your CDF. This is the definition of your single variable CDF. So that means what now? When in a CDF, in a multivariable CDF, when one of the variable goes to infinity, that means you will get a single variable CDF of the other variable which is not infinity. Okay. Similarly, now say you have x is a variable and y is infinity. When y is infinity, you will be getting fx of x. When both are infinity, you will be getting the answer 1. Here if you observe, when both are minus infinity, the answer you will be getting is 0. And here when both are infinity, the answer you will be getting is 1. Okay. So these are some properties of your what? CDF. Similarly, we'll go ahead and try to check some properties of your PDF. Okay. So first we'll see what actually is this PDF, that is Bivariate PDF. Now, before going into this Bivariate PDF, we already know that our single variable PDF is given by something like this, which is small f of x is equal to nothing but d by dx of capital F of x. What is capital F of x here, friends? It is the CDF. What is small f of x? It is the PDF. So how do you get the PDF? By differentiating your CDF. Okay. So, and one more very important relation from your module number 1, that this whatever you can see right now, these are inverse pairs. That is, if I want a CDF, what I will do? I will put an integration sign for your PDF. This has been in detail explained in the first module. So remember these two relations. Okay. So going ahead, so what actually is this your Bivariate PDF? That is, we'll try to see what actually is this Bivariate PDF. Now, when we speak of bivariate, it means that there are two random variables. Which are the two random variables? One is x and another one is y. So what did we do here, friends? When there was only one variable, we differentiated your CDF once, d by dx. Now we have two variables. So that means what now? We need to differentiate it twice. So that's why you can see here it is dou square dou x by dou y. And with respect to what? With respect to our bivariate CDF. So what is a bivariate CDF? One is fx, y with and your x comma y. That's what we have found here. Please observe if the definition of your bivariate CDF, that is fxy into the bracket small x comma small y. So the same thing we are using here. It is nothing but fxy into bracket small x comma small y. Okay. Now one very important thing here is we can use our two-dimensional unit impulse functions to represent your derivatives of whatever discontinuities which will happen in CDF. Okay. Now it means that, like say for example, there are some discontinuities. There will not be some continuities and you will get some discontinuities. And if you have some discontinuities, then we can use our two-dimensional unit impulse function. We have two, if you remember, we have two functions, friends. When we deal with CDF and PDF, they are your unit impulse, right? Another one is step function. So whenever we have discontinuities in the derivatives of the CDF, then using unit impulse function, we can represent those discontinuities. That is what this line means here. Okay. Now, if you want to see how your CDF would look, just see here. This is what is your PDF. You can observe it clearly, more closely. You can just see that it is nothing but your unit impulse. These are nothing but your unit impulse. These are impulses. They have drawn the impulses. If you can see here, these are our impulses, right? Okay. So that means what now, friends? Whatever you can see here, these are nothing but your your PDF, which is nothing but your impulses. Now it is a two-dimensional. Why it is two-dimensional? Because there are two random variables. One is that's why I've taken here. One is X plane and another one is Y plane. So using that we have drawn this diagram. So what is this? Remember always when we draw impulse, it is PDF. It is PDF. Okay. Similarly, we can draw our CDF as well. So this is our CDF, friends. I'll just zoom it. Now you already know that your CDFs are represented by step function. You can see the steps here. You can see the steps here. Now again here, why we have shown such diagram? Because it is two variables. That's why one is X plane and another one is Y plane. It is represented along the X axis and as well as along the Y axis. Okay. So this is done. Next, we'll try to check upon your properties of PDF. Properties of CDF are over already. Okay. Always remember, friends, the first property of your bivariate PDF is it is non-negative. It will never be minus value. It will never be minus value. It will be always a positive value, which means that it will be always greater than or equal to 0. And if it should be greater than or equal to 0, the condition is your X and Y must be between minus infinity to plus infinity. Okay. Another major property of your PDF is, if you remember from single random variables, that we say that area under the curve of a PDF is always equal to 1. Now the same thing has been represented here. Instead of area, we speak of here volume. Why volume? Because we are speaking of XY plane. So always remember, for a bivariate PDF, the volume will be equal to 1. That means when you integrate your PDF, its value will be equal to 1. So why double integration, friends, again here? Because we have two variables. Which are the two variables? One is X and another one is your Y. That's why one will be with respect to X, the other will be with respect to Y. And when you integrate your PDF, the answer you will be getting is 1. Okay. So this is the one more very important property. So first property is it is non-negative. The next property is the area under the curve, which is nothing but volume, is always equal to 1. Okay. Next is the inverse relation for your equation number 2. Okay. So what is equation number 2? So here we have our equation number 2. So what is inverse relation, friends? It is nothing but you need to put the integration signs here. Since we have dou square, that means we will be putting here two integration signs. So if you can observe here, it is nothing but our two integration signs. One is minus infinity to X, another one is minus infinity to Y. Okay. So one is minus infinity to X, another one is minus infinity to Y. Now what we will be doing now? We will be doing the integration with respect to U and V, which is nothing but du and dv. So the first integration is with respect to u. So that's why I have written here first integration will be with respect to u. Once you integrate with respect to u, the second integration will be with respect to v. Okay. So this is very important. That is the inverse relation. Inverse relation is nothing but, since you have there dou square, that is 2 times differentiation. Here you need to do what now? 2 times integration. That's all. Okay. Now suppose if I want to find my joint PDF, if I want to find a joint PDF, please observe very carefully. So this is nothing but, whenever in joint PDF, if one of the values, if I want to get a joint PDF, when I have a joint PDF and if I want to obtain a individual CDF, see here friends, here I have a joint PDF, here I have a joint PDF, that is PDF of two variables X and Y, and from this I want to get a individual CDF. So individual CDF, how you represent individual CDF? It is capital Fx of X. So if I want to find that, then I have to assume one of the values would range from minus infinity to plus infinity. That means it is taking all the values of Y, whatever the Y values are there, it will take all the values of Y, ranging from where? From minus infinity to plus infinity. Okay. Now that means what now? First integration is minus infinity to X. Why? Because its limit, it is from minus infinity to X. But what about our Y friends? Y is nothing but it is minus infinity to plus infinity. Why? Because we have taken its range that it is minus infinity to plus infinity. That is, we have assumed it is taking all the values of y. So this is one case. The other case could be what now? Here we have assumed y is ranging from minus infinity to plus infinity. We could also assume that x could range from minus infinity to plus infinity. In that case, there will be small change in the limits. If you can observe here, I have taken x outside, that is nothing but minus infinity to plus infinity. Okay, and what is y then? It is minus infinity to y. Why? Because it's a finite thing. Okay, and what we are doing, what change we have done here? First, we will be integrating with respect to y. That's why we have written here dy and then dx. That's why when I write here first dy, I need to take its limits, which is minus infinity to y. When I write here first dx, I have to take the limits with respect to x. That's why we have written here minus infinity to x. Okay, friends. So this is the difference in between the integration of this and this. So here what we'll be getting? We'll be getting the CDF of x, that is one variable CDF. Here what we'll be getting? We'll be getting the CDF of y, that is nothing but one variable CDF. Okay, so this is all for today's class. Guess so I have it's been a lengthy class, so please try to go through it very slowly, and if you have any doubts, please ask. Thank you.